creators of Apache Flink. And it offers the DA platform, which is a supported Flink distribution. That's basically all I wanted to say on behalf of my company. Let's get started with the actual talk. Streams are everywhere. This might sound a bit surprising in the beginning, but if you think about it, most of our data sources from which we gather data basically produce data in a streaming fashion. So, for example, consider like a network of sensors, a set of mobile devices, or the clickstream from your web servers. This data they produce is produced continuously, and so it's only logical that you as the consumer of this data would like to process the data continuously and as fast as possible as well. So without adding any artificial delay to it. Because by doing that, you can realize some cool applications, like, for example, doing fraud detection when processing credit card transactions, doing online aggregations to fuel your dashboards with the latest BI, or to do online live recommendations when people are on your website, for example. In the past, a usual processing pipeline looked the following way. So you have a system where you ingested the data and collected the data, and once you've collected enough data and batched it up, you scheduled a periodic ETL job processing this data. The result of this ETL job was then stored somewhere and made available for an external query service, for example. The problem with this traditional batch analytics approach is that you basically add delay. So you don't process the data when it arrives in your system, but after some time, which is bad because you might lose a competitive advantage compared to other companies because you cannot react fast enough to changing events. In contrast to that, streaming analytics allows you to do online aggregation of the data as it arrives. So whenever a new event comes in, you can basically update the internal state, make it available to an external system, like, for example, a dashboard, then have the latest result without any delay. Furthermore, if you think a bit broader, then batch processing is effectively also stream processing of where you only have a finite stream. So if you read a file from disk, for example, you also consume a stream, right? So the only difference is that to real stream processing, that it's finite. So in that sense, stream analytics or stream processing subsumes batch because it generalizes it. In order to do proper stream analytics, you need a stream processor which can give you the following requirements. First of all, we are interested in processing large volume streams. So the stream processor we are using should give you a high throughput to cope with the incoming data and not adding any delay because we cannot keep up with the stream. Then usually you are interested in having consistent and correct results, also in cases of failures because they are unavoidable. And also in case that events which arrive at the system are out of order, which is usually the case if you, for example, consume data from mobile devices, and there it's easily possible that a mobile device, for example, has no connection to send you the data. And once it regains connection, it will send you the data a bit delayed. And last but not least, in order to write different applications and have enough a system which allows you to express very different applications you need and advanced Windows support, because to do aggregations you usually have to define windows on your input stream. But I come to that later. A different form of stream processing is complex event processing, which has the basic idea that you are analyzing a stream of input events and try to find patterns in it. And based on these matched events, which fulfill the pattern, you basically derive new events, which are usually called complex events because they are derived from the input events. With this paradigm, you could, for example, try to detect like malicious behavior in your network, or if you have like a algorithmic trading system, you could define rules when to sell or buy stocks, depending on certain patterns you see in your input stream. So that's quite cool. In comparison to streaming analytics, however, it poses some different requirements to a stream processor. Because usually you don't process large volume streams, but you want to process the data as fast as possible, because that could give you a competitive advantage. So we need a system which can also give you low latency results. And again, since we want to have correct and consistent results, our stream processor should give us exactly one semantics as well as event time support. Well, one of the stream processors which fulfills exactly this set of requirements is Apache Flink. You might have heard of it. It is it basically fulfills the requirement that it can do low latency processing as well as cope with like high throughput. It with this Gendy Lamport-like checkpointing mechanism, it can give you exactly one processing guarantees. It understands event time. Thus, it can deal with out-of-order elements. And it has a powerful windowing mechanism, which you can use to construct complex applications. And its core data stream API is available in Java and Scala. All right. For the remaining part of this talk, I want to present you Flink's CEP and streaming analytics APIs using the example of an order process which we want to track. So let me first introduce this use case. So we have three actors: the customer who sends orders to a retailer, the retailer which upon receiving this order processes this order, creates a package which is given to a delivery service, and this delivery service sends the package back to the customer. And at all of these three stages, like receiving an order, giving the package to the delivery service, and finally delivering the package to the customer, we generate events. An order event, a shipment event, and a delivery event. And we record all these events in our event stream. This event stream basically reflects the process we are trying to track. So here I've written again the three types of events we can observe. The order, shipment, and delivery event. They all have an order ID to identify them. They have a timestamp when they occurred, and they have a constant string field to identify the type of the event when we use stream-SQL. All right. Now, since we have our event stream, like modeling our order process, we can ask questions about it and try to answer them using stream analytics. In the past, how you would have done it is probably using a batch system which well, batches the incoming data up and triggers repeatedly a query against this finite by changing data set. And in the wake of well, processing the data, you would usually join it with some other data sets to produce the overall results. In contrast to that, in the stream analytics case, we don't have a query which is executed multiple times, but we have a standing query, like a query which gets constantly fed in the newly arriving data and produces continuously new results. And that way, we can basically compute aggregates on streams, on potentially infinite streams. Well, now you might raise the question, wait, how can we actually compute aggregates if our stream is endless? Doesn't it take an endless amount of time? Well, if you want to obtain the final result of an infinite stream, then yes. But what you can do is you can basically split the stream up into finite chunks, or what we call windows. And these windows are usually, the input stream is usually split by time into well, finite sets on which you can aggregate. There are multiple types of windows available. The two most popular ones, or well, also basic ones, I have to admit, are the tumbling windows, which split the input stream up into fixed size chunks, either by a number of elements or by time, such that each window is directly followed by the next window. So, for example, if we see in the, well, next to the tumbling windows bullet point, there we see this stream, which is split up into consecutive pieces. And if we now want to calculate the sum of this window, we simply have to add the elements together. A different type of window is the sliding window, which is similar to the tumbling window that it is of fixed size, but this time the windows can overlap, such that elements can be a part of multiple windows. And here it's important to highlight that again we need event time support to assure that that the events are assigned to the proper windows, because when the events are ingested in your system, they might be out of order. So that's an important feature of a stream processor to finally well, produce the correct results in the end. All right. How can we apply this to our well, scenario? So let's assume we want to count the number of orders we've received per hour. Well, the first thing to do is we have our input event stream, and we split it up into well, finite windows. Here we use the tumbling windows, which have a length of 1 hour. So we split the input stream up from 2 to 3, 3 to 4, 4 to 5, and so on. And then within each window, we count how often we've received an order, which is indicated by the letter symbol. So in the first, from 2 to 3, we have received 1 order, from 3 to 4, 2 orders, and so on. All right, that's conceptually quite easy, I guess. How can we express this logic within Flink? For that, Flink supports well, stream SQL, and we could write the following SQL query to compute exactly the result I've shown you on the previous slide. So what we do is we select from our event stream, say that the status column of the rows we want to consider has to be equal to received, which means that it is an order event. Then we group by a tumble window. This is basically splitting the event stream up into finite windows of length 1 hour. And then the only thing we have to do is apply our aggregation on it, that we simply count the elements in each window. And, well, something else which might be new to you is the tumble start keyword, which gives you the starting timestamp of the window, basically. That's our output. And that's really easy to do and also doable in a declarative way, right? Okay. Now, as you've seen how we can specify stream SQL queries, how is this actually well, realized within Flink? To parse and validate the stream SQL queries, we use the Calcite project. The parser and validator produces a Calcite logical plan, which can also be generated by using Flink's internal table API, which is a more embedded DSL to specify like these stream SQL programs, but not only stream SQL, but also proper SQL queries. That is for the system. It doesn't matter whether it's like a stream underneath or whether you are processing a static table. Having obtained this Calcite logical plan, it's given to the Calcite optimizer, and from there we basically generate Flink, native Flink programs. So if we are processing static tables, then it would be translated into a dataset program, and if it's a stream table, it would be translated into a data stream program. And that's how Flink executes these programs. All right. Now we've seen a bit how like streaming analytics works with Flink. Now let's take a look at the complex event processing, or finding patterns in our streams. For that, let's quickly reconsider our initial use case, which is the order process we want to track. And now, what we want to find out is we want to get notified whenever our delivery service is delayed, like creating an alert if the delivery doesn't happen in time. That way, for example, what you could do with that, we could send the customer like a message that it's, well, delivery won't arrive this day, thus increasing or improving the user experience. Or we could also use it to assess the reliability of our delivery service. All right. So it's interesting information. So how could we do that? Well, first of all, we would have to define some SLAs, how long like a delivery can take. And we also want to do the same for the internal processing of the order in our warehouse. In order to model like a successful order processing, we introduce the process success message, like a failed order processing is represented by a process 1 message, and the same applies for the delivery. There we have a delivery success and a delivery 1 message. All messages, again, have like an order ID to identify to which order they apply, a timestamp when they occurred, and in case of a success message, how long it took to go from one stage to another. Okay, so since this is might have been a bit too much theoretical, let's take a look at a concrete example, what it actually means for our event stream. So what we want to find out now, given our input event stream is whether like an event, for example, the green first order event is followed within a given time by its succeeding event, the shipment event. If that is the case, as we see on the slide, then we want to generate this process success message, recording the time it took from the one stage going to another. If, however, like in the case of the blue parser symbol, the symbol is not followed by its succeeding event type, the delivery event, then we want to generate this alert saying, look, the delivery is delayed. Maybe you should tell the customer that he is not waiting at home. The way we can calculate these new complex events is the following. First of all, we define our pattern for which we look in our input stream. So in order to calculate the process success and warn messages, we say that whenever we see like an order event, the letter symbol, which is followed by a shipment event, within a given time, then it's a successful order processing. And if not, then we generate our alert or warning, which is the lower branch. The way it is specified in Flink is the following way. We use the pattern class and call the begin method on it, telling the system that we expect an event of type event, which gets the name received and has an additional constraint that it is of subtype order, so that the first stage of the pattern is only matched by an event if it's an order event. Then we say that after we've seen this order event, then we want that the next element called shipped follows on that, such that the shipped event has a status field which is equal to shipped, which is basically the equivalent to saying that it's of subtype shipment. And this whole thing should be matched within, or should be found within a time frame of 1 hour. The followed by API call basically says that the second event does not have to directly follow after the first one. So an arbitrary number of other events can appear in between. All right. After we've defined our pattern, we can apply it to our input stream. And since we want to generate the success and warn messages for every order individually, we key by the order ID and then give it the pattern. And last but not least, we have to generate our new complex events, which we do by specifying a select clause where we provide a timeout handler, which is the first function, which is given a partial pattern, which is only has been matched partially, and the timestamp when the timeout occurred. And then, as a result, we generate our process one message, giving it the order ID and the timestamp. And the second function which we provide to the select clause is the select function, which is called for a fully matched pattern. And there we calculate the duration in the last line, where we subtract the received timestamp from the shipped timestamp, giving it the order ID and outputting the process success message. That way we basically can generate our alerts. All right. That's also quite nice and already gives some insights into our process. But wouldn't it be even more interesting to combine our CEP results with stream analytics? For example, we could ask the questions: how many delayed shipments occurred each day? That again could be used, for example, to come to the conclusion that our current delivery service is too unreliable, so we have to switch it. Or Another question we could ask is how long does it take on average to process the orders in our warehouse? And this information, for example, could be used to try out different internal processing models to see which one performs better. So let's try to do that. Well, yeah. So what we're trying to do now is we combine the CEP results with streaming analytics. So what we have here is our data stream of either delivery warning or delivery success, which is the output of the select clause from the previous slide, okay? Here, we're only interested in the delivery warnings. So we filter out the delivery success messages because we only want to count how many delivery warnings appeared. Next, in order to make the data stream usable from within a SQL query, we have to convert the stream into a table and register the table at our table environment, basically giving it a name to reference it from within our SQL query. And this is exactly the same query you have seen before. We select from our delivery warnings, group it by a tumble window of length 1 day, and then simply count how many warnings each window contains. Okay, this is, I think, already quite nice, but still feels a bit clumsy because we are mixing here Java programming or Scala programming, to be precise, with writing SQL queries. So wouldn't it be even nicer if we could combine both? And that is actually something the Calcite community is currently working on. They are integrating an Oracle proposal for pattern matching into their system. And once it's integrated, also Flink will support it. So if we want to answer the second questions, like how long does it take on average to process an order per day, we could do it completely declaratively, as you can see on the slide. So you would, how you would do it is you select from a nested query, which produces the CP results. And the nested query, what it does, it selects from our input stream, and applies the match recognize keyword on it. Within this function, we say that we partition by an order ID and order it by timestamp because we want to process the complex events per order, right? Then we define a pattern which says, consists of a start event followed by an arbitrary number of other events and an end event. And this pattern shall appear within 1 hour. Since this pattern by itself would match any sequence of at least 2 events, we further specify in a define clause that the status column of the start event equals received, meaning that it is an order event, and the status column of the end event equals shipped, such that it's a shipped event. Having found this kind of pattern, we can calculate the duration it took going from one stage to another stage in our process by simply subtracting the start timestamp from the end timestamp. And additionally, we output the timestamp of the end event. And that's basically the result of our nested query. And in our outer query, what we do, we group by a tumble window with a length of 1 day and use the average aggregation to calculate the average duration of our processing. And that way, we basically have answered our second question in a much nicer way. Yeah.
Tumble and tumble start are different because?
Yeah, the tumble basically tells we want to have a tumble window, and the tumble start says I want to have the timestamp of the starting timestamp of the tumble window I'm in.
So it uses.
For that, you have to define a tumble window to give the tumble start a meaning.
And while we wrote it, did you consider using window functions for and window statement for instead of the tumble?
That's the way the cal site defines windows, basically. It is how you specify it within SQL. Yeah.
Other stands for what in the pattern? The word other. In the I'm sorry, can I ask you a question regarding this? The other, the word other, okay, with the asterisk.
Other, yeah.
It stands for what in the pattern?
Other events, it's
a keyword. It's a keyword in this.
No, it's just a name. Other cleany star means just any sequence of events.
All right, thanks.
But we can come back to it like in the after I've shown you my last slide, the conclusion, and then talk a bit in detail about it. So this brings me to my last slide, or almost last slide, to the conclusion. So what you've seen today is that Apache Flink, as a stream processor, is able to handle CEP as well as analytical workloads alike. It, I think, has some intuitive APIs to solve some advanced problems easily, and allows you to get quickly started. And by combining CEP with streaming analytics, we are able to implement a kind of new class of applications to extract even more information from a data. So, meaning creating more value for a company. And with that, I'd like to thank you for your attention. If you find Flink interesting, I can recommend you following Apache Flink Twitter account to stay up to date, or Data Artisans, the company. Then there's a book, Stream Processing with Apache Flink, which I can recommend to the interested reader. Currently, the first 3 chapters, I think, are available online, and the others are following soon. If you want to learn more about Flink, there will be a dedicated Flink conference taking place in Berlin, September 11th to 13th. It's a really fun conference, so I can also recommend that. And if you think that Flink is a cool project, I like to work on it, and I would even like to get paid for it, then you should consider applying at Data Artisans, because we are currently actively hiring new people. And yes, thanks a lot for your attention. Yes?
Slide 22.
22.
Yeah. I can shout.
That's 22?
22. Slide 22, please.
That is slide 22?
That was not.
That's 23?
21.
And that's 31?
Yeah, this one.
Oh, that one.
I guess. So those strings, like that begin, then you define the type, and that string, it refers to the attribute of a type class.
You mean the begin received?
Yeah.
No, that's basically giving a name and like an identifier to the first event, which matches the pattern, because in the timeout handler and the select function, you basically reference these events by like pp received, so that you basically get the received event out of it. Because pp and fp are a map of string event
all right.
pairs. Yeah.
Hello. Yes, my question is, I mean, looking at it from an enterprise perspective, the subject is complex event processing, and when we try to do it declaratively within a really gigantic SQL construct, first, if the logic is complex, the code will become really, really complex and hard to manage. So previous approaches have been to somehow externalize the rules aspects of it and separate it from the windowing and event processing aspects. So how do you look at that problem? So do you think this approach of combining logic with business rules is the way forward?
Well, I think that if you have a problem which is, I mean, if you have a problem which is simple enough to be expressed in a combined way, it's nice to have, because surprisingly easy use cases well, try to be tackled by companies. That's what we see. So that's a value by itself if you offer, like for these use cases, a well-integrated way to solve it. If things should become too complex to manage, I mean, I don't know how you've solved it by separating the like if your input to your SQL query is basically some kind of pattern you want to find in your input stream and then feed it to your stream, you somehow I mean, you can separate it by first of all, I mean, doing it first the CEP part and then feeding it into your SQL query. Or, I mean, if you have it like here, it's basically the same, just a bit more like combined. So, of course, the inner parts can grow quite complex, but at some point you have to define the patterns, right? And you have to somehow extract it from the input stream and then give it to something else to process it. So. I think that one way or another you have to define the logic, right? Whether it's like all within one statement or to have like as before, like program part doing the CP thing and then the streaming analytic thing. It's basically the same for my perspective. Just that for some people, I think it's nicer to do it that way because they don't have to learn. Like a programming language because they can specify it declaratively. I don't know whether if you answered your question, but.
So it's also another way perhaps to build microservices, really small business logic rather than.
Well, if you do it that way, then you basically don't have the potential to optimize the complete query, right? If you separate the different parts of it, then you don't have a holistic view on it. So the optimizer cannot potentially do things which it could do if given the whole query, right? But of course, that's one way to well, break down complexity, right? Yeah.
So this is all lovely. Do you have any like preferred way of visualizing results of these kinds of queries?
That's basically up to the user. What Flink gives you is, at the end, it's a table or a data stream of results. You could use, I mean, for example, one way to visualize results is like writing them out in a database or to some Kafka topic, for example. We could also use, I mean, Zeppelin, for example, it's integrated with Flink to I think even with streaming results, you can visualize them. But that's like independent of Flinklets. So that's, yeah. think it's more concerned with the processing part of the data.